Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we are going to discuss a few results that have to do with MGFs, moment generating functions, and Poisson random variables. These results will be useful when we analyze data from a Bayesian perspective and the data being analyzed has a Poisson likelihood. Okay, let's begin. So the first result will be this. Maybe you did something like this in sta360, but let's do it. It will take just a few minutes and it will show you again that trick that we have been using a lot here in this course of when you have an integral or a series, the trick of completing what's inside that integral or that series, making that right inside that series or integral sign a legit probability distribution. Okay, so anyway, here we go. If y has a Poisson distribution with parameter mu, then what I would like to show, what we're going to be showing, is that the MGF of y is given by the following expression: e to the power mu times e to the power t minus 1. Okay, that's what we want to show. We want to basically derive the formula of the MGF for a Poisson. Okay, so proof. Proof. By definition, right? Remember what's the definition of the MGF? So it's an expected value, right? The MGF for the random variable y is the expected value of e to the power t times y. Okay? So, in this case, right, we know that a Poisson random variable is discrete. So what we're going to have is an infinite sum, a series, right? And we know that the support for a Poisson is, the possible values for a Poisson are 0, 1, 2, 3, up to infinity. Okay? And then, since we want the expected value of that transformation, we want e to the power ty times the probability mass function. So we know that the probability mass function for a Poisson with parameter mu is mu to the power y divided by y factorial times e to the negative mu. Make sense? Okay. Then what we're going to be doing is a little bit of algebra. We're going to be trying to simplify this. So first, note that this guy here doesn't depend on y. So we're going to pull that guy out. That will be our first move. Got it? No problem? Okay. Now, how about we combine these two terms, right? So we could do this instead, right? Let me write that down here. So instead of e to the power ty times mu to the power of y, we are going to have this e to the power t, and then we combine these two guys. It's the same, right? But that is going to give us a different perspective on this problem, right? Let me just make it look nicer. That's the same, right? Let's make a change of variable here. Let lambda be this guy here, mu times e to the power of t. Okay? So if we do that, right? Let me copy paste this. If we do that, then you'll see what I mean when I say that that changes the perspective we will have about this problem. We go, lambda to the power of y divided by y factorial. That looks like almost like the probability mass function of an exponential, but of a Poisson, but without the exponential term, right? If I wanted to have a legit Poisson, I would need e to the negative lambda, right? That exponential term. But that would be a constant. That doesn't depend on y, right? So I could multiply by that exponential term here, e to the negative lambda. And if I did that, and I'm doing the sum over the entire support for Poisson with parameter lambda, then that would be 1. So that's easy to do, right? But if we multiply by this guy, e to the negative lambda, well, let's multiply by its reciprocal, and in that case we're just multiplying by a 1, and that is not illegal, mathematically speaking. So again, see that trick of trying to complete expressions inside either integral signs or in this case, if you want to find a series, right? If you're able to find here something that is a legit probability mass function, then you know that if you're doing the sum over the entire support of the random variable, that is just a 1, right? So now what we have here is that the MGF is just this guy, right? That's the MGF of your Poisson. And let's go back to what lambda is. It represents this, right? So we have the product between those two exponentials, but lambda happens to be mu times e to the power of t. We do a little bit of algebra. That's the same as e to the power, let's factor out that mu, right? So it would be the same as mu times e to the power t minus 1. And that's it. That's the MGF for a Poisson. Okay, so we're done with result 1. Okay, let's do result 2, and that will be also easy and quick to show. So now, instead of being interested in a single random variable, right, now we're going to have 2. So let y1 and y2 be independent Poisson random variables. And both of them will have the same mean, with mean mu. So they are what you can call IID, independent and identically distributed. Okay? Okay. So now what we would like to do is finding the probability distribution of transformation of a function of them. Function that we are interested in is the sum of those two random variables. Okay. Okay. So solution: how we are going to find the probability distribution of y1 plus y2. Well, in sta360 you learned a few different approaches to finding the probability distribution of a function of random variables. One of them is the MGF approach, the MGF method. And the basic idea is, well, find the MGF of your transformation and then compare that MGF that you ended up with the list of those MGFs that you know for popular, for famous probability distributions. If it's in your list, guess what? Then the distribution of your new random variable, your transformation, is the one that matches with your list. Make sense? With the one in your list. Okay, so that's the idea. Okay, so let's do that. So let's define u. We're going to be using the letter u to refer to that new random variable, y1 plus y2, right? And we're going to proceed as we did before for the first result. By definition, the moment generating function of now this variable u is going to be just the expected value of e to the power du. Okay? So now what we have is, by the way, we defined u is the same as y1 plus y2, right? Okay, there we are. Next, let's do a little bit of algebra. So let's work a little bit on that exponent that's the same as t times y1, t times y2. Let me get rid of that bracket. I don't want it anymore. There we are. Next, we could express this as a product of two exponentials, right? That's the same as e to the power t times y1 times e to the power t times y2, right? Now, here is where the independence is really important. Since y1 and y2 are independent, the expected value of a product of independent random variables, or the product of functions of two independent random variables here, right? Again, the expected value of a product of expected values, and it could be just themselves or functions of themselves. The thing is that y1 and y2 are independent, then these functions e to the ty1 and e to the ty2 are also independent. Okay, they inherit the independence of y1 and y2. Okay, so bottom line, that is going to help us express the expected value of that product as a product of expected values, right? And when we see that expected value, we go, oh, well, that's by definition the MGF of y1, right? So this is by definition MGF of y1. That is by definition, the second term is by definition the MGF of y2. And remember that y1 and y2 have the same distribution. They are both random variables that have a Poisson distribution with the same parameter mu. And from our result, from our first result, that's the MGF for a Poisson with mean mu. So we have e to the power mu times et minus 1 times that. Again, these guys have the same distribution. Okay? So in the end, what we have is that the MGF of a sum of two Poisson random variables with parameter mu is 2 times mu. Well, e to the power 2 times mu times et minus 1. And then that implies, right, when you look at it, you go, oh, so let me use mu star for 2 times mu, e to the mu star times et minus 1. Oh, that's the MGF of a Poisson with parameter mu star, right? Make sense? Okay, so what we have shown here is that by the uniqueness property of MGFs, you must have a Poisson distribution with parameter 2 mu, right? So by the uniqueness property of MGFs, we conclude that U has a Poisson distribution with parameter 2 times mu. Okay? Now, this is going to be a homework problem, but let me just write that down. Say that instead of result 2, we had something that reads as follows. Result number 3. You have y1 y2 dot 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 oops, nope, yn, they are independent and identically distributed, right? Poisson random variables with mean mu. Now I want you to find the distribution of y1 plus y2 plus y3 up to yn. If you had to guess, what would you say it is? And then we could go back to what we did here. Y1 plus y2. Let's define u as y1 plus y2 plus y3 plus dot 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 yn. You would have something like this. You would have a sum with more terms, n terms, right? You would do a little bit of algebra here. Independence will be useful. Instead of 2 terms, you will have n terms, right? So, right? Instead of 2 terms, here you have n. So you will be able to show, basically just following the same steps for result number 2, that the probability distribution for that sum is going to be a Poisson with parameter n times mu. Make sense? So try and do that later tonight, okay? Just for fun. It will take just 5 minutes. Okay? So let's summarize what we did here. So first, we found the MGF of a Poisson random variable, right? It was given by that expression. We did it because the second result has to do with the distribution of a function of 2 random variables that are Poisson. And thanks to the MGF approach, to the MGF method, we were able to show that the distribution of a sum of 2 independent Poisson random variables with mean mu, guess what, has a Poisson distribution as well, and the parameter is going to be 2 times mu, right? And more importantly, later tonight you guys will show this, that the sum of n independent Poisson random variables with mean mu has again a Poisson distribution, but with parameter n times mu. And that result will be useful for an example that we're going to talk about later. We're going to analyze data coming from Poisson distribution, data with Poisson likelihood, and that result that the sum of Poisson random variables also has a Poisson distribution will be useful. Okay? Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.